Well, hello there, ladies and gentlemen. Here's what we're going to be talking about in this lesson today. We're going to be talking about polygons and angles within and around polygons. That means interior, exterior, central angles. Here's what we're going to do. We're going to learn what those are: interior, exterior, and central angles. We're going to learn that if we divide a polygon into non-overlapping triangles, we can learn about the sum of the interior angles, and we can also learn about the individual angles of a regular polygon. We're also going to learn that the sum of the exterior angles is 360, the sum of central angles is 360, and we're going to learn how to calculate the sum of interior angles of any polygon whatsoever. And we're going to do all of this in a way that each of these ideas is interconnected and easy to recall. So let's get to it, shall we? Let's start off with just a point. Let's say this point is the center of a circle. We know that the circle has 360 degrees within it, correct? So now let's start dividing this up. Let's take that center point and draw a single radius, and let's rotate that radius by 45 degrees. You'll see why we're going to do this in just a second. So we're going to continue this all the way around the circle. Now, 45 degrees does divide evenly into 360, 8 times, right? So if we do this all the way around, what we end up with is 8 angles, all of 45 degrees. Now look, if we take these intersection points between each radius and the edge of the circle and we start connecting them, well, we have ourselves a fancy, regular octagon. It's funny to say fancy and regular because those sound kind of like not the same, right? Now, each of these angles that goes from the center of the circle to the vertex of the polygon is called a central angle. So this is a central angle right here. All of the central angles of a regular polygon, they add up to 360 degrees. Do you see? So what a central angle is, just to make sure, is if we take the center of a regular polygon and we connect a segment to consecutive, two segments to consecutive vertices of the polygon, then what we have done is we've created a central angle. So this octagon has 8 central angles. Regardless of how many sides it has, the number of sides will be the same as the number of central angles, and the sum of those angles is going to be 360 degrees. Because of that, if you had a regular polygon and you were asked, hey, what's the measure of the central angle? All you'd have to do is divide that 360 degrees by n, which is, of course, the number of sides. So, for example, let's say we had a regular hexagon and we were being asked, hey, what's the measure of the central angle? Well, hexagons have 6 sides, so n would be 6 in our fancy formula right here. N stands for the number of sides. So 360 divided by 6 is 60 degrees. The central angle of a regular hexagon, 60 degrees. Boom, done. Now let's talk about interior angles, shall we? So first of all, we hopefully are very familiar with the fact that the sum of the interior angles of a triangle is 180 degrees. And maybe you did a project like this in middle school or something where you took a triangle, random triangle, and you colored each of the angles a different color, and you started rotating them around and copying that triangle, and then you found out that these do in fact make a straight angle together. All 3 of them are supplementary. Right. So that is a key fact that we're going to use to talk about the interior angles of a polygon. So what the interior angle is specifically is it's an angle created by consecutive sides of a polygon. So if we had this hexagon right here, we have consecutive sides like this right here and this right here. Those make an interior angle. And of course, the number of interior angles in a polygon is the same as the number of sides, n. So this hexagon has 1, 2, 3, 4, and then of course 5, and wonderful number 6. So this has 6 interior angles, right? Now, how could we tell what all of those interior angles add up to? We know a triangle has 180, but what about a hexagon? Man. So here's what we're going to do. We're going to take this hexagon and we're going to divide it into non-overlapping triangles. So what we're going to do is we're going to connect vertices in a way that the whole shape is divided into triangles, but not in a way that they're overlapping in any way. So let's do that. So here's one triangle. Do you see I just connected these 2 vertices? That's 180 degrees inside that triangle. So this angle, this angle, this angle all add up to 180. Let's do that again. Now, this angle and this angle and this angle add up to 180 as well. And we have one more line we can draw that makes 2 more triangles. So each of these triangles has 180 degrees. There are 4 of them. 4 times 180 is 720 degrees. So I don't know exactly what this angle here is, or this angle, or this, or this. But I do know that the entire hexagon is broken into 4 triangles, and each of those triangles has 180 degrees. 180 times 4, 720. So all of the interior angles of this hexagon add up to 720. So what about a pentagon? Well, let's do the same thing. Let's divide this pentagon into non-overlapping triangles. We have 1, 2, 3 of them. 3 times 180 is 540. So the interior angles of this pentagon add up to 540 degrees as well. And we could do the same thing with a quadrilateral. And I'm hoping you're starting to see the pattern here. You see a quadrilateral has 4 sides, 2 triangles. 6 sides, 4 triangles. 5 sides, 3. 4 sides, 2. Well, turns out that pattern holds true. Whatever the number of sides are, well, there are too few triangles. So if we had a 20-sided polygon, we'd have 18 triangles within. So 18 times 180 would tell us exactly how many degrees are inside that polygon. So interior angles would be made. So here's an interior angle right here. It's made by this side and this side. And if we add all 4 of these, we know that that's going to be 360 degrees. So we can do a formula from that, right? So 180 times n minus 2, that is going to be the sum of the interior angles of any polygon. Now remember, the 180 comes from the triangle, and the reason we're talking about triangles is because we can take a polygon and cut it up into 2 fewer triangles than the number of sides. So whatever the number of sides is, we have 2 fewer triangles inside of it. So what about the sum of the interior angles of an octagon, for example? Well, an octagon has 8 sides, right? So 180 times 8 minus 2 is 1,080 degrees. Now, does it matter if the polygon is regular or irregular if you're talking about the sum of the interior angles? Well, it turns out it doesn't matter. Let's take this irregular octagon right here. If we cut it up into non-overlapping triangles, we have 6, which we expect. That's 2 less than the number of sides. So, boom, we're done. So the truth is, the way it works is the sum of the interior angles of a polygon is the same. We use that formula 180 degrees times the quantity n minus 2. We do that whether it's a regular or an irregular polygon, right? Now, what if it was a regular polygon and we wanted to find a single interior angle, right? How could we do that? Well, let's explore this a little bit. Let's say we have this regular decagon. That's 10-sided. Well, we know that there would be 8 triangles inside. Each triangle has 180 degrees. So we would have 1,440 degrees would be the sum of all of the interior angles of this decagon, right? Now, because this is regular, what that means, it means all of the sides are congruent to all of the other sides. It also means all of these angles, all of these interior angles are congruent to each other. So there's 10 angles, they're all the same. We know they all add up to 1,440. So since they're all the same and there are 10, all we would have to do is just divide the sum by how many angles there are, and we have 144 degrees per angle. So if you're being asked to find a single interior angle of a regular polygon, all you got to do is figure out the sum divided by the number of sides. So that gives us this formula right here. 180 times quantity n minus 2, and you take that total, divide by n. Now, once again, just to make sure we understand why this works, let's just look at the numerator first. This is the sum of all of the interior angles. And the reason that works is because there are 2 fewer triangles inside of a polygon than there are the number of sides. Each triangle has 180 degrees. And we can divide that total by how many sides there are. If it's a regular polygon, because they're all the same, and boom, we're done. We figure out what each one of these angles would be worth. All right, last topic. Let's talk about exterior angles. Let's look at this fancy hexagon right here. If we take a side and we extend it, what we have is an exterior angle. This is an exterior angle right here. Now, the number of exterior angles is the same as the number of sides. So this hexagon right here has 6 exterior angles. Do you see? Now, let's say we wanted to figure out what each of these was. And let's say we were going to talk about this being a regular hexagon. even if it was irregular, an interior angle and an exterior angle are they're collinear. They make a straight line. And so that means they're supplementary, right? So that makes 180 degrees between the two. So if we wanted to figure out the measure of angle B, right, we could do that in a couple of ways. So let's say that we don't know any other facts about exterior angles yet, but we can figure out what this interior angle would be right here. So let's say this is a regular hexagon. We can't assume it. It has to be told to us. So let's say we know this is a regular hexagon. We can figure out that A is 120 degrees because there would be, if you figured out the total, 720 degrees would be all of them, divided by 6 is 120. Now, if this is 120 and they make 180 together, then this B has to be 60 degrees, right? So you could just use some simple algebra if you had to write it out. But either way, this is a straight angle. This is a collinear set of angles right here. They're supplementary, add up to 180, right? Now, if it's a regular hexagon, these are all 60 degrees. There's 6 of them. That makes 360 degrees total. Turns out that's always the case. The sum of the exterior angles of any polygon is always 360 degrees. Man, that's a lot of information. We're just going through this super fast. So here's what we covered, right? We're going to do a practice problem in just a second. So here's what we learned. We learned what an interior angle is, what an exterior angle is, and what a central angle is. We learned that we can take a polygon, divide it into non-overlapping triangles, and that gives us a lot of information about the sum of the interior angles, which we can use to figure out a single interior angle if we know that the polygon is regular. So we also learned that the sum of the exterior angles is 360. The sum of the central angles is also 360. And we learned how we can calculate the sum of any interior angle of a polygon. And man, we just killed it. We nailed it. So I think we got all of that there. So here's what I'd suggest. This practice problem right here, I would look over your notes as you're working through this. Everything you need to answer this question, to figure out what the measurements of angles A, B, C, D, and E are contained in the notes that you would have taken from this lesson right here. And then number 2 is a little bit of goes back to some triangle stuff. So this is a tricky one right here, finding the area of this triangle right here. So if you figure out the angles and you know that the side length is 4, then you can figure out the area of this triangle. So anyway, I hope this has been helpful. Hope it's been useful. Man, the thing about geometry that's tricky is that you have all of these facts and ideas, and one of the things you have to do is you have to look at a shape and you have to recognize, oh, I know something about this, or maybe I know something about that, and then put all those things together to be able to answer the question. So anyways, you guys are doing wonderful. Hope you're having a great day, and I'll talk to you later.